In the intellectual crucible of the early 1990s, physics found itself at a profound and bewildering impasse. The classical edifice of Newton and Maxwell, a monument to deterministic causality, stood in stark contrast to the strange new quantum rules emerging from the study of the very small, Max Planck's discovery of energy quanta and Albert Einstein's subsequent description of light as discrete packets, or photons, had established a bizarre duality. For electromagnetic radiation it behaved as both a continuous wave and a collection of discrete particles. This conceptual schism was most sharply illustrated by Niels Bohr's model of the atom, a brilliant yet deeply unsatisfying hybrid. Bohr postulated that electrons orbited a nucleus in specific, quantized energy levels, making inexplicable leaps between them, is condition for stable orbits. That the angular momentum of an electron must be an integer multiple of the reduced Planck constant was an ad hoc rule, mathematical prescription imposed upon reality, with immense predictive power but devoid of any underlying physical justification. The world of physics awaited a unifying principle, a conceptual key that could unlock this quantum enigma. It arrived in 1924 from an unlikely source, a doctoral thesis submitted to the Sorbonne by a young French aristocrat with a background in history. Louis de Broglie's dissertation, which urges sur la théorie des quanta, or research on quantum theory, stands as one of the most audacious and consequential documents in the history of science, a work of breathtaking intuitive synthesis that proposed a symmetry for the universe so radical it would forever alter our conception of matter itself. De Broglie's intellectual journey was grounded in the very paradoxes he sought to resolve. He was profoundly influenced by the twin pillars of early 20th century physics, quantum theory and special relativity. From Planck, he took the fundamental relation connecting energy and frequency, expressed as energy equaled Planck's constant times frequency. From Einstein, he inherited two monumental ideas. The first was the photoelectric effect, which treated light as a particle with energy and momentum. The second was the deep equivalence of mass and energy, immortalized in the equation energy equals mass times the speed of light squared. De Broglie stared into the heart of the wave-particle duality of light and asked a question of sublime simplicity and immense consequence. If a wave can manifest as a particle, could a particle exhibit the properties of a wave? He perceived a universal symmetry in nature, one that demanded this duality extend to all physical entities. His guiding inspiration was a profound analogy from classical physics, the parallel between Pierre de Fermat's principle of least time for optics and Pierre-Louis Maupertuis' principle of least action for mechanics. For centuries, these two principles had described the paths of light and the paths of particles using similar variational logic. De Broglie suspected this was more than a mathematical coincidence. He believed it was a hint of a deep, underlying unity between the propagation of waves and the motion of. The central argument of his thesis unfolds with compelling logical force. De Broglie began by associating an intrinsic frequency with a particle of matter. For a particle at rest with mass m sub 0, its rest energy is given by Einstein's relation, S sub 0 equals m sub 0 times the speed of light squared. Following Planck, de Broglie assigned this energy a corresponding frequency, nu sub 0, such that nu sub 0 equals m sub 0 times the speed of light squared divided by Planck's constant. This frequency represents a sort of internal clock for the particle. The situation becomes more complex when the particle is set in motion. For an external observer, the particle's total relativistic energy increases, which would imply a higher associated frequency. Simultaneously, Einstein's theory of special relativity dictates that the moving particle's internal clock, as viewed by the stationary observer, experiences time dilation and thus appears to tick more slowly, implying a lower frequency. This apparent contradiction was the first great hurdle. De Broglie's stroke of genius was to resolve this paradox by postulating the existence of a new kind of wave, what he termed a phase wave, that accompanies the particle through spacetime. He demonstrated mathematically that this phase wave always remains in phase with the particle's internal oscillatory phenomenon. A startling consequence of his calculation was that the velocity of this phase wave is greater than the speed of light, given by the expression v sub phys equals the speed of light squared divided by the particle's velocity. This seemingly physics-defying result could have been a fatal flaw. However, de Broglie showed with further rigor that the physically meaningful velocity, the speed at which energy and information are transported, corresponds to the group velocity of a packet of these phase waves. This group velocity, he proved, is precisely equal to the velocity of the particle itself, a value always less than or equal to the speed of light. The particle, in this new vision, are constructive interference, the localized concentration of a whole spectrum of underlying. From this sophisticated relativistic framework, de Broglie extracted the relationship that would become his most famous legacy. He showed that the wavelength of this associated matter wave, which we now call the de Broglie wavelength, is given by the simple and elegant formula lambda equals Planck's constant h divided by the particle's momentum p. This equation connected a quintessential wave property, wavelength, with a quintessential particle property, momentum, through the universal constant of quantum action. Having forged this powerful conceptual tool, de Broglie immediately turned it upon the great unsolved mystery of the Bohr atom. He envisioned the electron orbiting the nucleus not as a simple point particle, but as a wave propagating along its orbital path. For an orbit to be stable, he reasoned, the electron's wave must interfere with itself constructively. This requires the circumference of the orbit to be an integer multiple of the electron's wavelength. The condition for such a standing wave is expressed as n times lambda equals 2 pi times the radius r, where n is a positive integer. By substituting his own formula for the wavelength, the equation becomes n times Planck's constant divided by the electron's momentum equals 2 pi times the radius. A simple rearrangement of terms yields the product of the radius, and the momentum equals n times Planck's constant divided by 2 pi. Since the product of radius and momentum is the definition of angular momentum, this derivation resulted in the exact quantization condition that Bohr had been forced to postulate years earlier. In a moment of supreme intellectual triumph, Wifterius' rule of quantum bookkeeping was revealed as a natural consequence of the fundamental wave nature. The reception of de Broglie's thesis was, to put it mildly, one of profound consternation. The idea that a solid, tangible object, like an electron, possessed a wavelength was so counterintuitive, so alien to the prevailing physical intuition, that his doctoral examination committee was left in a state of academic paralysis. The panel, which included the distinguished physicist Paul Langevin, recognized the mathematical coherence of the work but struggled with its radical physical implications. In an act of intellectual prudence, or perhaps desperation, they forwarded the thesis to the one mind in Europe who might be equipped to judge such a revolutionary proposal, Albert Einstein. Einstein's response was swift and decisive. He saw immediately the deep insight and logical consistency of de Broglie's argument, famously writing to his colleague Hendrik Lorentz that de Broglie had lifted a corner of the great veil. Einstein's powerful endorsement secured de Broglie his doctorate and gave his theory the credibility it needed to be taken seriously by the broader physics community. The ultimate vindication, however, came from the laboratory. In 1997, 2 independent experiments provided stunning confirmation of de Broglie's hypothesis. At Bell Labs in the United States, Clinton Davison and Lester Jerram observed that a beam of electrons scattered by a nickel crystal produced a diffraction pattern, a hallmark of wave behavior. In Scotland, George Paget Thomson, the son of the discoverer of the electron, passed a beam of electrons through a thin metal foil and observed distinct interference rings on a photographic plate, analogous to the patterns produced by X-rays. The wave nature of the electron was an experimental fact. For this singular insight, Louis de Broglie was awarded the Nobel Prize in Physics in 1929. A mere 5 years after submitting his thesis, one of the fastest such recognitions in the history of the prize. The most profound and immediate legacy of de Broglie's work was its role as the direct progenitor of modern wave mechanics. In Zurich, the Austrian physicist Erwin Schrödinger became captivated by de Broglie's idea of a matter wave. While de Broglie had provided the conceptual framework and the fundamental wavelength relation, he had not specified the mathematical law governing the evolution of this wave in space and time. Schrödinger took upon himself the task of discovering this law. Aided by the formal analogy between classical mechanics and geometric optics, he sought the wave equation, whose solutions would be de Broglie's matter waves. In a burst of creative genius in early 1926, he formulated the partial differential equation that now bears his name. The Schrödinger equation is the cornerstone of non-relativistic quantum mechanics, a law as fundamental to the quantum world as Newton's laws are to the classical world. It describes the behavior of the wave function, a mathematical object whose squared magnitude represents the probability of finding a particle at a given point in space. This conceptual leap from de Broglie's physical wave to Schrödinger's probabilistic wave function marked the beginning of the Copenhagen interpretation of quantum mechanics, a view that described reality in fundamentally probabilistic terms. Without de Broglie's foundational insight that particles are guided by waves, Schrödinger's path to his equation would have been inconceivable. De Broglie provided the physical intuition, the tune, and Schrödinger provided the precise mathematicals. The influence of de Broglie's thesis extends far beyond fundamental theory. The understanding that particles like electrons have wave properties led directly to the development of powerful new technologies. The most prominent example is the electron microscope, which exploits the extremely short wavelengths of high-energy electrons to achieve resolutions far surpassing those of conventional light microscopes, allowing scientists to visualize the very architecture of molecules and viruses. Intriguingly, de Broglie himself grew increasingly uneasy with the probabilistic turn that quantum mechanics had taken. He was dissatisfied with the Copenhagen interpretation's abandonment of determinism and clear physical pictures. He believed that the wave and the particle were both objectively real entities, a concept he had alluded to in his earliest work. In the later decades of his life, he returned to this idea, developing what is now known as the pilot wave theory or the de Broglie bone theory. In this deterministic interpretation, the particle has a definite position at all times, and its motion is guided by its associated wave, which acts as a pilot. This alternative framework avoids many of the philosophical paradoxes of the standard interpretation, and though it remains a minority view, it has continued to attract interest from physicists and philosophers of science concerned with the foundational questions of quantum reality. This later work reveals de Broglie's lifelong commitment to a rational, intelligible picture of the physical world, a quest that began with his revolutionary thesis. In the final analysis, Louis de Broglie's research on quantum theory is more than a successful doctoral thesis. It is a testament to the power of philosophical symmetry and physical intuition in scientific discovery. Emerging from a background that blended the humanities with science, de Broglie possessed a unique perspective that allowed him to see a unifying harmony where others saw only discordant phenomena. His proposal of universal wave-particle duality was an act of profound intellectual courage. It provided the crucial conceptual link between the old quantum theory of Bohr and the modern wave mechanics of Schrödinger, thereby launching the most significant transformation in physical thought of the 20th century. The thesis stands as a perfect example of a theoretical work that was both deeply conservative, it appealed to classical principles of symmetry, and wildly revolutionary. In its ultimate conclusion about the nature of existence, it demonstrated that the electron, the very symbol of a discrete particle, possesses the ethereal characteristics of a wave, and in doing so, dissolved the rigid classical distinction between matter and energy into a more subtle and far more profound unity. De Broglie's work taught us that the fundamental constituents of our universe are stranger and more wonderful than we had ever imagined, entities that defy simple categorization and demand a new, more holistic language for their description. The thin volume he submitted in 1994 did indeed lift the corner of the Great Veil, revealing a quantum reality whose beautiful and enigmatic structure continues to challenge and inspire scientists to this day.